All right, what we're going to be talking about is the South Georgia Rift Basin, which is the southernmost rift basin along the eastern North America, right here. So here's the South Georgia Rift Basin. As far as the timing, let me go ahead. There were some questions about, source rocks and things like that. The timing, as far as what it, being a late Triassic, is only based on its relationship to the magmatic intrusions that occurred around 200 million years ago. We tried to do paleo, but we found only an inertite. So there's very little organic material in here. In fact, there's very little mud. But these are the ages, and these are from publications by Martha Withjack, and I know you Triassic rift people are probably quite familiar with Martha's work. But for those of you who are not into rifts, let me just go over the mechanics, and this is just a model of what Martha came up with. So here we have Pangaea, or part of Pangaea. Africa and North America are still together. But as we're getting extension, we're creating essentially a place for rifts to form. So we're getting these extensional faults causing these rift basins here. And this would be, because this is down in Georgia. But as we progress and start to widen the Atlantic, we have the spreading center here. Instead of extension, there's more pushing along the margin, and we cause actually a reverse and pop-up, or the inversion. And I'll just explain that a little bit more. So this is the model. So we have here the start of the breakup of the continent. So you can see these flow arrows here. So we have extension, creating the rift basins. But then as the Atlantic is opening up some more, there's more force here on the trailing edge, and we actually get a compression, and we get inversion. So rifting, inversion, and this is the drifting, where the continents are pulling apart, and you have the Atlantic here. So now I learned all this in school, but working on this project, I got to relearn it again. So it was exciting for me. Plus, I used to work with Martha, at City Service. Okay, so I was told that some of you folks wanted to see some seismic, so here we go. This is going to be about it. This is from an article by Atkin Tunde in 2003. Essentially, he reinterpreted some, size data 6 lines that were done, I think. I'm not sure when they were done. But this is this line here. This is the rift basin. There's Florida, Georgia, South Carolina. And essentially, he interpreted these sort of half province. So the orange here are the rift basins that we're going to be talking about. Now, the green is the coastal plain sediments, essentially late Cretaceous to Quaternary sediments. And most of these, except for a few limestones, are essentially unconsolidated. So you have these Triassic here. A lot of this is basement. It's metamorphic, granites, things like that. And then here you're filled with these sediments. Now there were some wells that were done. Here's a cross-section here going from C to D. So from here, C to D. And this is in Georgia. There's some thick sands here, a couple kilometers. This is one real close to the well that we eventually drilled. This is the Norris Lightsey. This was drilled by Texaco in the early 80s. And we can see over 2 kilometers of sand. And these are shales and also diabase dikes, or basalt dikes. And then over here is wells that were cored by the USGS to look at the basalts. And here we have a couple hundred meters of basalt. And this is talking about basalt. This is also from Martha Withjack. So this is the camp is the Central Atlantic Magmatic Province. This occurred after the formation of the of the Triassic rip basins. Essentially, and this is supposedly is the biggest aerial occurrence of volcanic activity of basalts that has ever occurred. But here we have North America. All these little lines here are basalt dikes. And this pink area here that starts as our study area, this is based on seismic, is a basalt flow. In fact, a study in the late 80s by McBride et al. And again, this is based on the cores by USGS, but that was only one location. But this was the extent that he interpreted for the basalt. Unfortunately, that did not pan out to be, but that was the early thoughts. So what do we have here? This project, this was done jointly with actually the prime contractor, but the person that got this grant. This was done with a DOE grant for carbon sequestration. That was the reason for this. And so what we have here is we have a lot of sand, as I pointed out on those cores, or the lift logs, and then we have this big basalt. So the theory was that you have the cap rock here and you have these big sands, and I know this is the oil patch, but I put this CO2 diagram here. Essentially it shows, this is from an AAPG special publication. So, okay, so here we have time going from 1 year to 10,000, and this is trapping, the types of trapping, so structural and stratigraphic trapping. Lower probability, you need in a CO2, you have to at least keep it underground for 1,000 years, and hopefully more. But you can trap it with structure or residual trapping, but you really want to get solubility. And eventually you want to get precipitation out into the sandstone. And we were going to do the studies on this. We're going to do a special core analysis to look at the solubilities of the CO2 in these sands, and also try and interpret how much precipitation was going to come out. But this is supposedly a deep saline aquifer, and you want to get it dissolved into these fluids. But not a very high percentage of CO2 goes into these things. So you need a lot of rock, you need a lot of porosity. So that's what we were looking for. So the study, as far as the seismic, Mike Waddell, who is the investigator at South Carolina, he is still doing more seismic and doing more interpretations. These are the lines that were used from that new seismic that was run in the study area. That's the location of the Texaco well. This is the location of the USGS well. And here's the location of the well that we drilled. It was called the Rizer 1. The main operator was Schlumberger, and they also did the downhole logging on this well. Now originally we wanted to get down to 9,000 feet, but unfortunately we lost the well at 6,200 feet. I think it was an intersection of a possible fault and a dike, and after some weeks of trying to get through it, it was abandoned. So we were left with 57 feet of conventional core. Now Weatherford was involved in catching the core. We were supposed to catch about 300 or 400 feet, is that right, Mike? About that. But instead we got 57 feet and about 108 sidewall cores. Because we didn't have the core that we wanted, we went in and just cored the bejesus out of this as far as the sidewall cores. So this is what the study was based on. Okay, now my main MOS or whatever specialty is sedimentology. I put the MOS in there since tomorrow's Veterans Day. So this is a core, a very good looking core to study. You can see the cross bedding in here. It's relatively coarse grain. Usually I'm looking at mud rocks and I need a microscope. I did not need a microscope for this. This is the lithology description of the graphic description. So the yellow is sand. You can see there's a lot of sand. A little bit of mud at the base. The wider it is, the coarser grain it is. We're dealing with medium to coarse grained sands. But I think even in the back of the room you can see the cross bedding here. This is probably some overbank alluvium. A little bit closer look from that same area. This is a thin section. So it's 5 millimeters down here. You can see the big clasts, big grains, poorly sorted. A lot of these clasts are actually micrite. They're carbonate. Further up in the core, you can see it's a little bit finer grain. It's fine grained sand. You can see ripple beds in here. There's even some flazer bedding. Now, based on the geographic reconstructions from Withjack and a lot of other folks or co-authors, there was no contact with, marine environment. But you can see the burrows in here, so we must be dealing with a lacustrine setting. Okay, so you can see these tubular-looking things, a little bit of mud, but these are burrows. Kind of very similar to the vertical burrows or horizontal burrows. Must be in a sort of a lacustrine standing body of water. I don't think it was just fluvial. Another thing that supports a standing body of water, and you can still get fish in rivers, of course. But here's a fish part, probably a scale. This is about 100 microns here. So, and there's, you can see about a medium grain sand, but there are critter parts in here. Unfortunately, not the critter parts that you can date, but there are signs of lacustrine influence. The other thing, this is from a rotary sidewall core taken up section, and all these things marked CC are carbonate class, they're micrite. So there's a lot of, and there are some shell fragments recrystallized in here. So here's sand, and also this is stained pink, this is a calcite cement. So it's telling us we have a fluvial, coarse grain, but there's standing body of water and there's micrite. Now this is not really all that odd. I know last year Mitch Harris was in here giving a talk about carbonates and rift basins. So this is a common thing. This is a model from the Flagstaff Formation out in Arizona. It's Paleogene. Essentially, I think this is what we're seeing. You have alluvial fans coming in, probably reworked with rivers going down the axis of the valley. Then you have these lakes out here with carbonates. So fairly typical. The thing that would be different in our case is we don't have very much mud. This is mud in this model with the channels. Here is a litholog. This is yellow for the Rizer one. The green is sort of a muddy siltstone. So there's not very much in the way of fine-grained sediments. And again, there is more material down here, but we didn't penetrate it. But even in the Norris Lightsey, which went down 1,000 or so more feet, it still was mostly sandstones and not mud rocks. Okay, so we're going to look at a little bit more closely at what the sandstone looks like. And the first thing I want to point out is that blue is porosity. Not out here, but that's porosity right there, a little bit right there. This is a plutonic rock fragment, so from granite. There's this is a mica chloride, a few sedimentary rock fragments, metamorphic rock fragments. The scale here is 800 microns. But you can see there's not very much in the way of porosity. If we look at a ternary diagram for my geophysicist friend, I'll try and remind him. This is feldspar, quartz, and rock fragments. So this rock is mostly a lithic arkose. So the reds are rotary sidewall cores, and the blue are conventional cores. Yes, I got that. Got that right. So we're going from a lithic arkose to feldspathic litharonite, an immature rock. Now this is a ternary diagram showing the percentages of sedimentary rock fragments, volcanic rock fragments, and metamorphic. Mostly metamorphic. And these sedimentary rock fragments, when our petrologist did this, he lumped those micritic clasts in there. But I think they were mostly contemporaneous muds that were deposited. So but still they're sedimentary, so that's the way they were lumped. But it's mostly metamorphic rock fragments. Oops. So that one, okay. A little bit closer up, here's 100 microns. Here you can see the big metamorphic rock fragments. This is a potassium feldspar. It's been stained yellow. A little bit of porosity here, and that's about it. More metamorphic rock fragments. Now the importance of this is another picture. This is in plain light. This is in cross nickels. This is a big metamorphic rock fragment right here. Now, one of the reasons why we did this is we were trying to figure out where these sediments were coming from. And the most likely source is, I'm not sure if you're familiar with the East Coast, but there's a thing called the Piedmont. You have the metamorphic rocks and granites and things like that. And this is the most likely source. So here is South Carolina, Georgia, North Carolina. So this is a good source terrain, very close, nearby, for these sediments to come from. Now you remember, the continents were separating. There was some thought, well, maybe these things are coming from Africa, but we're pretty sure that the sediment is coming right off of the Piedmont. And also they're poorly sorted, not very well rounded, didn't travel very far. Okay, so now let's go into reservoir properties. This was one of our better, these are from rotary sidewall cores. This is from about 4,000 feet. Here the blue is porosity, and you can see there is some pores. In this particular core, a rotary core, was about 12% porosity. The perm, 5 millidarcies. That's not bad. It wouldn't be bad if this was like our worst one, but here's another core taken from 5,400 feet. And this is more typical, and you can see the blue is also, in this case, porosity. But there's no blue in this particular photomicrograph. Again, the scale is 800 microns. This one is 2.9. The permeability is 0.0045. So this is our average. And again, we had like 100 rotaries and 20-some from the conventional core. And the average porosity is about 3.4%, and the average permeability is 0.05. Now, in order to do special core analysis, if you wanted to do this, which we were supposed to do, you need at least 0.2 to get anything reasonable as far as millidarcies. So things weren't looking good there. In fact, I can still remember when Robert Fu is our touchstone petrologist. He's my go-to guy for what the hell is this rock fragment. I remember him coming into my office and he said, these rocks are a lot deeper than they are today. This particular rock is from 4,600 feet. You can see all these stylites here, one there, one there. It's permeated with stylites. You can see all these grains, not all, but a lot of them have been dissolved. And that usually doesn't occur at 4,600 feet. So, we were supposed to do special core analysis, and we were supposed to figure out, how much CO2 we can put in this rock. But we said, well, we're not going to put any CO2 in this rock. We're going to say this ain't going to happen. So we had to figure out what we're going to do. So the new objective was, why is this reservoir quality so poor? Because we had to come up with some answers. Can we predict reservoir quality in other portions of the South Georgia Rift Basin? Because we only had one well. So that was our new goal. So we came together and designed a program based on this limited data that we had, which I think a lot of you can appreciate, having a limited amount of data and having to project that to the whole basin. Well, we did our homework, and I said I'd probably read this before, but the basins up here had also experienced. Now remember I mentioned in the model of the Triassic, you have the rifting, and then you have from extension, then you have the compression and inversion, and then you have the drifting. Well, in the Taylorsville, then the Bay of Fundy, past studies had shown, and this again is from Withjack, that their models, the basins had subsided and then bounced up. So our goal was, well, did this happen to our particular basin? So how are we going to approach that? A lot of these folks had outcrops in a lot of data points. We only had this one well, 57 feet of core, and a whole bunch of rotaries. So we looked around and said, well, at past studies and in the literature, and there's one way of doing this, and we wanted to see how deep did this core go, or this rock went. Well, one technique was contact index counting, is a modal analysis of the sandstones. Another thing was to try and come up with a burial temperature and look at the cements and look at the oxygen isotopes. Now, when I went to graduate school, one of my heroes was Cesare Emiliani, who first did the initial work on this, so I was sort of going back home to study this, even though I wasn't looking at forams. But okay, so what is the contact index or the tight packing index? These are things that were put together, well, Pettijohn, but Wilson and McBride had done a lot of studies in which we compared these two, our results to. But the CI is the average number of contacts for each grain counted. So you count 200 grains and then you count what you, or if you have a new geologist that happens to show up next to you, you go, hey, I got a great project for you. So, and the TPI is the sum of the average number of long, concavo-convex, and sutured contacts. Let me just go back here a second. These are the different types of contacts. So this is a sutured contact. This is a concavo-convex contact. These would be point contacts, long contacts, and so forth. This is a floating grain, all right? But I'll show you some examples of that. Okay, for instance here, this has been stained. The pink, you might not be able to see the color, but this is calcium, a calcite spar cement. So you can see these grains are floating up here, right? They're not really kind of touching the other grains. Well, the CI is about 2.5, and the TPI is relatively low. Down here, where there is no cement, there's many more contacts, and it's got a higher number, 4.6 and 3.5. And these are great numbers, especially if you're not the one that's having to do the point count.
Right.
Okay, this is another example here. You can see the calcite cement stained red. Relatively low numbers. I think this was the same, just a close-up of that. And then here you can see these are grains. Again, carbonate cement is red. There's very little carbonate. There's some quartz cement, which you can't really pick out here in this plain light photograph. But I think you get the gist. Higher the number, the more compaction. Okay, so we compared our results from this Triassic Rift Basin to the study that was done on the Wilcox and the Carrizo sandstones by McBride et al. And this is their data going from 2,000 feet to 14,000 feet. And this is our data here. Now this is plotted based on the actual depth, okay? This is the CI. Now there's, their CI numbers up here, they get fairly high at depth. All ours are up here because, again, we only have a couple thousand feet of rock. But our numbers, if you go down, actually look like they're coming in at about 10,000 feet. Now, if you look at their R squared, that's about 0.7. Ours is 0.2. We don't have very much data. We have 10 points. Might be 12. I don't know. I couldn't get her to. Actually, we didn't have that many cores to count. But so we have a limited data set. Okay, this is the TPI. Again, those contacts, types of contacts. This is their data, and this is ours. So our numbers are higher. So ours are at, let's say, 6,000 feet, but they kind of go off the scale. They didn't even get that high in numbers in the Wilcox and Carrizo. Just one way of comparing. So this showed, I think this is showing that these things were deeper and can kind of come up with a number. You know, a couple thousand feet or 3,000 feet or so deeper, or even more than that. Now you might say, Triassic Rift Basin, you know, this is subsiding too fast. You can't compare it with the Gulf Coast. Well, actually, if you do, they actually have very similar subsidence rates. I was surprised when I found that out. And in fact, some of the geothermal gradients close to thrust faults, there's higher geothermal gradients in the Gulf Coast than there is in our supposed geothermal gradient in our Triassic Basin. But I'm jumping ahead and haven't gotten there yet. But this is sort of a slide into temperature. Now, another way to tell how deep you are is by the temperature of the cements. But how do you tell the temperature of the cements? Well, Harvey Blatt, back in the 80s, he published this paper, and essentially looking at the O18 ratios. This was whole rock, so I think he dissolved the rock and did sort of wet chemistry on this. So just briefly, this would be granite. So it's going from, this is parts per 1,000, 6 to 12 for granite. And I won't go through all of these. But like chert goes from about 15 all the way to 35. The higher the number, the lower the temperature. Okay? So how do you get the temperature of the rocks? Well, again, the lady that Brittany Holland, who did the point counts, I stuck with the point counts. I was very lucky that she's a geochemist, and she showed up at my doorstep. She said, well, what about a secondary ion mass spectrometer? You can actually go in and measure the O18. I said, what? Yeah. And so she hunted up this machine. This is a picture of the machine from the University of Wisconsin, the SIMS machine. Essentially, it is sort of a, I don't know, it's got a long column, a huge magnet that takes a day to warm up, and I think it cost us $10,000 a day to operate it. So, but I thought this was, well, since it wasn't, actually, it wasn't my money. Well, it was my money. It was all your money, because this is a DOE-funded project. Okay? Right.
You're welcome.
All right, so what is this going to do here? So what do we do? First, how do we get this ready to do the analysis? First, we have to, in the thin sections, we had to find out where there was a lot of cement, quartz cement. We were looking at quartz and calcite. But then we had to identify, you know, is there one generation of quartz or two generations of quartz? So we got a hold of Kitty Milliman at the Bureau, and I said, can we go over and use your CLSEM machine? So we went and did CLSEM to find the quartz cements. And I'll show you some closer pictures. So we identified where the quartz was and that there were multiple generations. And then, you know, thin sections are kind of rectangular. We had to find the spot that we did the CL work on, put it into a thin section, and the people at Wisconsin cut it in a circle and put a standard right in the middle. That's what this is the standard. And you had to have your area that you wanted to sample within 8 millimeters of that standard. Because what they do is you zap 10 holes in this thing, then you go back and zap the standard to make sure your thing's still working. I lost a lot of hair in my hair was probably just as white before, but it was not easy to do. This is what it looks like. These are like 20 micron holes. These are the values here in yellow. These are the numbers of the sample. So you get a table, you know, where the values are from, and you also get some photographs. These are the numbers that coincide with the table, and these are the O18 values. Now I'll show you a little bit closer up picture. Probably would be better if the lights were lower, but I think you can still see it. Here, this is the grain. It's dark. This is luminescing luminescing quartz cement. You can see the straight lines here. The values here, a low number, this is a detrital quartz, so it was from a granite or something. This high number probably was an early cement. These are also cements here, 13, 16. These are values that shows that it's more than one generation, but also the CL also tells you that this is, a different generation than the ones that aren't fluorescing. So essentially we go transects and look at the values. This is another one, and this was the one that was done after 12 hours. This is what it is in plain light. A lot of these things are very angular. I looked at it and I said, this is probably cement. Well, when I did this transect, the only way you could tell what was a detrital grain and what was cement was by the values. You couldn't tell optically which was what. And what's happening, I think, is a lot of these things are squeezing, melting, dissolving, and there was a lot of things to scratch my head about. So this is the model that we came up with, or what you do with these numbers. So you have all these numbers. The high number is a low temperature. A low number is high temperature. So you plug it into a formula that gives you values as far as a temperature is concerned. That's using this particular, and when the paper comes out, you can read all about it. That's from Colleton. Now then you have to come up with a geothermal gradient to come up with depth. Now we could have used a 27 degrees C per kilometer that's currently in the East Coast, but we would have been down to the Moho. So we used, not quite, but it would be pretty deep. So we used a geothermal gradient of 40 degrees C from a study by Singh of the Taylorsville. And we came up with then the depths of, this is how we came up with the kilometers of depth. So here's the temperatures, and here's the depth. And what we saw was that we had 3 groups of quartz cements. This would be the shallowest, probably at about 2 kilometers, the second at about 2.5. Then the third was actually smeared, not grouped at all. Probably was created by gradual subsidence, dissolution by pressure solution, and then reprecipitation of the quartz cement. So we're able to reconstruct the depths of our various cements. No, you're not finding oil, but I'm giving you tools that you can look and see where you're at. We also did this on calcite. Here are the values here. This is a probably a detrital grain recrystallized. I won't go into detail here other than we could only measure one calcite because of roughness issues. We didn't have very much calcite. You have to polish the thin section very well. And if you have a lot of quartz, you can't polish the calcite and the quartz at the same time. So we had to do bulk analysis. But essentially, this is a comparison with a Kitty Milliken study of the Frio Formation, where I parsed out her cements, and again with depth going from 0 to 16,000 feet. This was her values. These were our values. Again, we had 3 groups. And again, except for this one, which is probably very early, these things appear much deeper than where they are today. So another line of support that these things were a lot deeper. So before I go into giving you the model and wrapping up, I'll just show you some more pretty pictures for Donald the petrologist over here. We have grains here, a lot of quartz overgrowths. You can see this fuzzy stuff here. This is chlorite, a lot of chlorite. And it's fairly early. This is an SEM photograph. Here, quartz growing around it. We had a lot of different types of clays. Another thing we had, these are orthogenic sphenes. I don't know if you've seen this, but sphenes, fairly large, so about 100 microns here. You can see calcite. The crystal edges here shows that they are cements. You know, they grew, they're autogenic. Kitty has mentioned autogenic sphenes in the Gulf Coast, but the pictures she shows aren't as big as our sphenes. So this is a detrital sphene. This is probably an overgrowth right here. We have anhydrite, and then we have chlorite and various other things. But again, porosity is blue. We still have no porosity. Interesting rocks to look at. Sort of the last thing that happened to this is this thing, these red lines here, these are diabase or basalt intrusions. This is a FMI done by Schlumberger. These are the beds here, or not beds, but the intrusions. These are thin sections. Theoletic basalts is what these are. So I'd have to go back and read it again. Don't ask me to spell it.
What's the scale on that,
Oh, this is
Jim? On the log.
Oh, on the log. Here, this is, let's see, what is that? 10 feet?
Sorry.
Yeah, I think it is. It could be 20 feet. Sorry, I can't think of it here. I think it's 10 feet. But you can see these are at a relative angle. We were hoping that these were going to be sills, but the fact that they're at such a high angle and the tadpoles out here are indicating the same, that these are probably relatively high angle dikes. And of course this, you can see the texture, these are definitely basalts. And the one way to recognize these on the log is they're also have low gamma. But petrographically, these are basalts. One thing that is associated with these basalt intrusions is that there's fractures all around them. And these are probably chill zones. So you have the intrusion, they got hot and then they cooled, and now instead of being sort of impermeable areas, they are actually avenues for water to go through. In fact, another set of dikes down at 4,100 feet. You can see here's some calcite. This is mostly clay. These are some phenocrysts of olivine that have been converted to calcite and fibolite. And the rest is clay. So actually, you're getting a lot more weathering along next to these dikes than you are getting in the actual sandstone. So now, concurrent with this, North Carolina had done a study because they were thinking about using these for injection wells. But when they did the studies on their dikes, they found the same thing, that these things were sort of avenue for groundwater to go through. Now, okay, we have these dikes. What about could this be influencing the diagenesis of the sandstone? Well, there was only one rotary sidewall core that was right above the base, down at 6140. In this thing, we lost the well at 6200. And this is a plain light photograph here, and that is 100 microns. I sort of call these biscuits. These are actually feldspars, but they looked cooked to me. They looked kind of like a biscuit. This is an SEM photograph. And this is an altered K-spar, and there's clays. Essentially, these things look like they've been baked, and they're fairly close to this. Probably was more of an extensive intrusion down the bottom. So what is the model? This is our model right here. So going from 250 million years ago to 200, and we're just using this date of 200 based on the models of Withjack. So deposition, then down to probably about 12,000 feet, and then at about 200 million years ago, we project that the basin was inverted. And then this is the present depth And we're sort of setting this for about 5,000 feet is where we're using as our key. So we have an uplift of kilometers of uplift. One thing about this is there's a whole lot of sediment that was above this that got eroded away. So maybe that's a reservoir someplace, but certainly, as I pointed out here, there are no reservoirs or storage areas in this particular part of the basin. So our diagenetic model, of course, compaction all the way through, at least until the inversion. So from up to 200 million years ago. First thing that happened probably were clays. I didn't describe those. Early calcite cement, then also other generations of calcite cement. Some evaporite cement. Probably there was dissolution. And then I created space for subsequent quartz cement and also for the chloride. But actually based on, when you look at cements next to each other, you have the illite and chloride, sphene, probably occurred before the initial quartz cement. Then you had multiple generations, as I pointed out in the 018 results, of quartz cements. And finally, probably dissolution by pressure solution and reprecipitation until eventually the thing was inverted. And then about the same time is where you had these intrusions by the dikes. So in conclusion, this basin, complex history. Study interval was buried deeper by 6,000 based on modal analysis, or at least 8,200 feet deeper. Now this is where this thing was inverted. Now possibly there's other part of the basins that weren't inverted, and maybe they still have rocks that might be porous, but other studies have shown that that little basalt layer isn't really as continuous as people had thought. So this is too poor of a reservoir due to compaction and cementation to consider as a repository for CO2. And the last conclusion is that the millions of dollars, we didn't get nearly enough of that, I'm sorry, but the millions of dollars that were spent on this probably could have been avoided if the Geological Survey of Georgia hadn't been disbanded and threw this particular sample away. And Texaco didn't give away their core, and it got lost subsequently. If we would have been able to look at these cores, we might have saved all of us a few dollars. Of course, we would have spent it on something else.
Right, right.
That's just something to consider. So the Canadians, those socialists to the north, they save everything, but then maybe they don't repeat studies like this. So I want to thank, of course, DOE, the funding source. I want to thank the Bureau for letting us use their system, and University of Wisconsin for, and I didn't go into the probe analysis, but for the use of their sims. If you ever get a chance to use one, it's exciting. It's kind of hair-raising and nail-biting, but it was interesting. I also want to thank my co-authors and Mike Waddell, who did the seismic and got me involved, and then all the others from Weatherford that helped out on this project. And I want to thank you for your attention, and I'm happy to answer questions. As the rock was subsiding, as the basin was subsiding, the calcite dissolved. Some places, where we got quartz cement in there, and maybe the places where there wasn't quartz cement is where there was too much chloride. Okay, so some of the rock has been completely compressed. There's no cement. Other places there is a lot of cement. So it's kind of, I think there wouldn't have been any porosity either way, unless you would have had maybe some mud rocks in there that could have held in fluids and kept the pores open because of the pressure. I mean, that's what's happening in the Gulf Coast, right? I mean, the substance, I was surprised, but I said, well, we need to write this up, and we're comparing this with the Gulf Coast, and we need to say some words. Well, they're not really similar, and then I looked and said, wow, it's the same substance race. But there you get some overpressuring. And here, even I think if you got overpressuring, the fact that these dikes came through, and the fracturing occurred very relatively early, I think you would have lost any overpressuring. And then plus there was not enough mud based on, now what I'm showing, that was a litho log based on cuttings. And, but there is not very much mud to stop the flow of fluids. So I think the fluids went through there enough to cement everything up. But yeah, there just wasn't enough fluid in there that was captured and like in the hydrocarbons to keep it from cementing up. Does that sound reasonable?
Yeah, you put overpressure in a basin, it changes things quite a bit as far as contraction, because you get this equilibrium contraction. Fluids are actually holding up the rock. In this case, with all those dikes in there, one wonders whether it's purely depth of burial and rebound is causing that, or whether a lot of it's just the dikes, the temperature of the dikes causing that.
Well, again, the only place that we've done also elemental analysis, and we did not see a lot of changes related to these dikes except when we got down to the bottom one. And I think that was relatively thick. We don't know because we didn't penetrate it. And that one rotary that I showed you was the only one that really saw evidence of cooking. And not the proper term to use, but yeah. So even the elemental analysis backed that up too. But my elemental person isn't here, so I can't defer to her. Yes?
Excellent presentation. I want to thank you. Question regarding the dikes. Did you have any opportunity to date the approximate age of intrusion?
Well, we looked at that, and we were 50 kilograms of, or not 50 kilos is about what we needed. We didn't have that in a rotary sidewall course. So no, yeah, we didn't. Yeah, because we could do zircons, but no, we had to rely as far as dates with Jack and the dates that were done on the flows. We just didn't have enough sample to do that.
So the ingoing assumption would be that it was fairly early while everything was buried in depth. And
well, again, we're basing that on with Jack and the 200-year, the regional studies that were done. So, yes, ma'am.
So do you think all Triassic basins up and down the East Coast have the same burial history as this one?
Well, based on this one and the Taylorsville and the Bay of Fundy, it appears, at least in those, I haven't. And Martha's waiting for me to send her the paper so she can check this one off too. Yes?
Excellent talk. By the way, doing CIs or TPIs is a hell of a lot of fun.
Especially when somebody else does it. No, yeah, it's
no, they're fun. They're fascinating. Did you try applying either the indexes against the 018 data?
Well, as far as cross-plotting that?
Yeah.
That's a thought. And we just sort of used them as corollary. So, we haven't got very much space that we're dealing with. We're only dealing with a couple thousand feet. So, that's why our, correlation stuff, or the, whatever it is, the R2 was so lousy, because we're not dealing with thousands, tens of thousands of feet. At least that's the reason that I'm thinking it is. We haven't got very many samples, and I think it was just using the two techniques and comparing them to see if they came up with the same results, because I didn't want to use just one. But. And
another question was there any correlation between the presence of orthogenic sphene and the basalts?
Well, the place where we found the sphenes, well, we couldn't identify any sphene that we saw. The one that looked like it was cooked. So it was so altered that, we couldn't really identify it. the way we initially, so Robert, who did the initial analysis, he thought these things were dolomite because they're highly birefringence, high relief. But when we looked at them in the SEM and we zapped them, all this titanium came out, we went, what's this? And then we saw it was autogenic. Well, I guess that's sphene. So, and we did microprobe on it, and it did turn out to be sphene on some of them. And we tried to date some of these sphenes, but again, I didn't really explain it very well, but the way this SIMS works is essentially you bombard it with I think it's with ions, I suppose would be, that's why it would be a secondary ion. But if your surface isn't completely flat, if it's rough, I think it's some of the timing issue is how you figure out what your ratios of O18 are. So if you have a rough surface, your numbers get screwed up. So the only autogenic sphene we had was like right on the edges of some detrital sphene, and the edges were too rough because the hardness between the sphene and the quartz made polishing. We polished them at Weatherford, not to get, and then they were repolished at Wisconsin, so it wasn't just our polishing. So it was just something that was part of the problem with this device. So, yes.
Did you see any differences in the O18 values above or below zones of severe stylization?
Well, we really didn't, bringing up some good questions. We'll have to go back and revisit that. But I think there wasn't pressure solution in every sample, so that's something to look at, yes. But I think that in the groupings of the quartz, that I think there's that one last bit of quartz cement must have been, well, I'm thinking that it's due to pressure solution, and that's how the quartz came. But there's no clay. I mean, like a lot of quartz comes from what is it, alteration of montmorillonite to illite, but we don't have that much clay to get the silica from.
Well, you've got to have a fairly cleaner sandstone before you can get stylites. They do not occur in very dirty sandstones.
Well, you have a lot of mica flakes in there. You do have some clays, so you can see. Well, there's clay that's being concentrated at the stylites, and you have the metamorphic rock fragments and some sedimentary rock fragments, but there's not a lot of mud in there. But I think there's just enough, and you squish it enough. But I'm a sedimentologist, so when we found out we had to do this diagenetic study, I said, oh no. But I think we use these very fundamental ways of doing it, and I think we came up with a halfway believable story. But we haven't put this out for peer review yet, other than AAPG talk. So I'll let you know in about a year when we start getting nasty notes. But, yes, sir.
Jim, you mentioned there's seismic identification of the diabase layer down there. Did none of these wells reach it?
There actually isn't seismic, and I talked to Mike, because these things are really too thin for him to see. And I would have shown some of his seismic, but he sent me, I said, give me an example of the flower structures that you were seeing. And all I could see, send me a seismic, and there's lines going here, lines going there. As far as interpretation, I said, no, I don't want to try and explain that. I'll let you do that. I've asked him if he can follow these, because he keeps calling a lot of these things sills. And he says he can follow them, but I don't know, these things are so thin, I don't know if you can see them in the seismic. So, but mostly we were depending that we knew that we hit a sill or something, because we were getting up volcanic material at the base of the core, or where we were drilling, where we lost the well. And then also, we got those. And then also the elemental analysis was pointing that too.
But you weren't able to correlate any of the areas he thinks he sees them to one of the wells?
Mike thinks he can do it. I'm not so sure. So, because I'm thinking that the FMI is saying these things are high angle, and I don't know how you're going to correlate that very far, because they're pretty high angle, so.
And another question, I was trying to tell from your chart, did most of the cementation occur on the subsidence cycle?
No, yeah, it all occurred, and I'm deferring to Robert. He said, usually.
Okay, now I see your arrows.
Yeah, if
Okay.
they're, yeah, I'm sorry I didn't point that out. So everything was occurring while it subsided.
Got it.
And conventional wisdom is that, you know, once you start bringing the rock up and you're cooling it off and decreasing the pressure, that essentially you've stopped everything. So, and I'll go by that. But, you know, the only thing we can come up with is the compaction and the temperature. So, yes.
Thank you, Jim. You know, as if your admonition weren't enough, I think I recall at a Legends Night that AGS has had for a number of years. I believe it was Burt Valley said when asked what he thought the most significant problem that our science and industry faces in the future. He said it was a loss of data. And he goes all the way across the board from seismic data, core, like that. And not that we want to spend more taxpayers' money. And it wouldn't be, because I think it would probably have to be in a different country. But if you went further along the rifting margin, south of where the South George Rift is, it'd be interesting to, if you had the information with the comparison, not only up the East Coast, but you know, further along the rifting margin. Because they ought to be younger.
Right. Well, yeah.
Where would you look for that next basin?
I had to ask Martha about that. So her diagrams only go to the southern part of the North American continent. So, and normally I'm a sedimentologist. I didn't want to do diagenesis, but I was forced into it in this particular case. Any other questions? Yes.
There's going to be some exploration in the Atlantic eventually offshore. Is there any way to use this data about the Triassic to influence how they look at the Atlantic?
Well, I think Martha's work on the regional probably, and yeah, just educating people. I mean, we use techniques that other people have used. I think this is the first time that SIMS, you can maybe correct me if I'm wrong, where the TPI and the CI were used in conjunction with the SIMS. So what I wanted to do in this talk was just to show you, if you're looking at a basin, you'll have limited data, but you have samples like this, and you want to know how deep your stuff was, that you might be able to do it using these techniques. So, but
Okay. Well, in recognition for you giving your talk here, it was a good talk. Special gift for you, Mr. Jim Rine. Petrified wood from the Miocene